All right, everyone, welcome to the Cumulative Review Packet number 8, video number 2, and we left off on number 9. So if I bring my calculator up here, and I bring this over, here we are, and I plug this in to my calculator, I would get, bring this down a little bit, I would start with 0.055, and I would divide that by 4. And then I would add 1. And then without rounding at all, I would raise that with a little caret to say answer raised to the 40th power. And then I would multiply all of that times 4,500. When I press enter, looks like my answer would be, and I lose it unfortunately, but I think it was, so 7770.47. 7770.47. Now it says round to the nearest hundredth. That is why when it said 0.468, the 8 rounded the 6 up to a 7. And this notation makes sense because we are dealing with money. So I started with $4,500, and if I compounded quarterly for 10 years, it raised to $7,770.47. Number 10, a car sells for $27,000. If the rate of depreciation is 14%, what is the value of the car after 8 years? Now that is one heck of a depreciation value. We're going to see some decreasing in this car value. Depreciation is really another word for decay, which makes me think that we are going to be using y equals a times 1 minus r to the t value. We don't have to use this equation because the money is being taken out once per year, and we don't have to deal with this n. And so if I'm thinking about what I have, my A value or my initial value is the $27,000. My rate is 14%, which as a decimal is 0.14, and the time that passes is 8 years. So if I plug that information into my equation, I would have y equals $27,000 times 1 minus 0.14 raised to the 8th. So if I bring my calculator back out here, and I first do what's inside the parentheses, 1 minus 0.14, enter, raised to the 8th power, then multiplied by $27,000. My final answer will be 8078.88, which again makes sense because I'm dealing with money or a value of a car. Check this out though. The car started off at $27,000, and at a high rate of 14% loss per year, my car went down to $8,078.88. That is a heck of a depreciation. That's very unfortunate. Again, please make sure when you buy a car, don't have a value this high. Please watch your rate. The next example is talking about the population at the Automotive Club of America, and it first had 21,500 members, and it grew. When I see the word grow, it makes me think exponential growth, which, before I read the rest of the problem, means I'm going to be using this equation, 1 plus r to the t, because growth and the addition makes sense. Looks like my initial value is the 21,500 people. The rate of growth is 4%, which is 0.04 as a regular number. The amount of time that passes from 2015, from 1970 to 2015 is 45 years. So if I plugged in that information, I'd have y equals 21,500 times 1 plus 0.04 raised to the 45th power. So if I bring my calculator out again, I would take 1 plus 0.04, and then I would raise that to the 45th power, and then I would multiply that by the 21,500 initial people. And when I do that, my answer is 125,585.27. So if I wrote that down here, I'd get 125,585.27. Now again, because we're dealing with people, the reason it says the nearest whole number is whichever whole number makes sense in the situation, because I can't have 0.27 as a person. I have 125,585 people. And just to check that again with the calculator, yes, that looks good. The next example also deals with growth and decay, and we're trying to determine if the following equations, just by looking at them, are exponential growth or decay, and then beyond that, we're trying to figure out what percent growth or decay we're dealing with. And so what I'd like to point your attention to is, again, I would like to, from the previous slide, write the growth equation and the decay equation. If I think about what I see here in this first equation, I notice that my base is bigger than 1, which means that this is exponential growth. And I notice that this base, 0.93, is less than 1, which means this has to be exponential decay. Now, that part you might recognize more from examples we've done. But the tricky part about this problem is figuring out what exact percent growth. And so because this is a growth equation, my eye goes here. And what I want to do is see if I can rewrite this equation to look like this. So instead of 1.76, I have to write it as 1 plus something raised to the x value or the t value. If you think about it, what do I add to 1 to get 1.76? Well, if I add 0.76 to 1, I would get this base, which means that my rate, or r, is the 0.76. And 0.76 as an actual percent is 76%. And so if you think about rewriting this equation in the growth and decay equation format, you can get the right answer. The trickier one out of the two is the decay, because I want my base to be 0.193, but I need to think about rewriting my equation as such. Because it's decay, I want 1 minus a particular rate raised to the t value or the x value or whatever. So if, in your calculator, you take 1 minus 0.93, I'm going to write a little note over here. 1 minus 0.93 is equal to 0.07. So if you think backwards, to get 0.93, I'd have to do 1 minus 0.07 to get to this, which means that this again is my rate, and so my percent or rate of growth is 0.07, which is really 7%. Graphing. Here we go. Complete the table of values and graph the points accurately. And then once we do, we need to answer some questions. So, if I would like to graph y equals 2 to the x plus 3, I need to plug in my favorite values here. So 2 to the negative second plus 3, 2 to the negative first plus 3, 2 to the 0th plus 3, plugging in for x each time, 2 to the first plus 3, and 2 squared plus 3. I'm going to start down here because, again, I think the positive exponents are easier. Unfortunately, that pattern that we noticed between the negative 2 and 2 and the negative 1 and 1 in class does not work if there's anything happening to the function like going up 3. So we're just going to have to do the order of operations here. So 2 squared is 4. So 2 plus 4 gives me an output value of 7. 2 to the first is 2. 2 plus 3 is an output of 5. 2 to the first is 1. 1 plus 3 gives me an output of 4. 2 to the negative first is really the reciprocal. So 2 to the first is 2. So 2 to the negative first is the reciprocal of 1/2 plus 3, which is 3.5. And then 2 squared is 4. So 2 to the negative second is the reciprocal, 1/4 plus 3, which is really 3.25. So if I graph all this information, I notice that my values are getting closer and closer to 3. I go from 7 to 5 to 4, 3.5, and then 3.25. So let's see what this looks like. Negative 2 up 3.25 would be right here. Negative 1 up 3.5 is a little higher. 0, 4, 1, 5, and then 2, 7. So if I'm thinking about connecting these dots, my graph looks like it's getting very close to 3, connecting all these dots and then shooting up here to infinity. So this is what my graph is going to look like, and in a different color, I would like to draw a dotted line here to represent the asymptote, which is the line that I'm getting really close to, but not touching. And so now if I want to answer some information about this, I look at my graph, and I notice that it crosses the y-axis at 0, 4. My asymptote, or the line I cannot touch, the line you cannot touch, is this horizontal line here. And you might remember from semester 1 that any horizontal line hits the y-axis. So the equation would be y equals 3, because that's the line I cannot cross here. My domain, my graph goes forever to the left and forever to the right. So it's negative infinity to positive infinity, because we always go left to right. The range is the y values and domain is x. So if range is y, we go from the bottom to the top. So the lowest value that this graph gets really close to is 3, and then the highest value is all the way to infinity. So that means that my range is from 3, parenthesis because I'm not touching 3, all the way to infinity. And yes, guys, there is a connection between the asymptote and the range. This is the line I cannot cross, and this is the same place that the range starts. Does the above graph represent growth or decay? Well, it's going to represent growth, because from left to right, the graph is increasing. My next graph is y equals 1/3 to the x. And so just like the last time, I am going to plug the numbers in for the exponent. So 1/3 to the negative second, 1/3 to the negative first, 1/3 to the 0th, 1/3 to the first, and 1/3 to the second. That looks like a 1, sorry about that. I'm going to start down here, just because again I think it's easier. So I'm going to start here. Remember that this is really 1 squared over 3 squared using exponent rules, which would really be 1/9. Because this function has nothing else happening to it, we can use the reciprocal pattern, that if 1/3 to the second is 1/9, 1/3 to the negative second has to be the reciprocal of 9/1, or 9. 1/3 to the first is really 1 to the first over 3 to the first, which is 1/3. And again, because there's nothing happening outside of the function, I can assume the reciprocal. So 1/3 to the negative first is really 3/1, or 3. 1/3 to the 0th is still 1. So this time my points are -2, 9. So we'll start up here. -1, 3. 0, 1. 1, 1/3. And then a little lower at 2, 1/9. So this time the numbers look like they are slowly getting closer to 0, but not quite getting there. So my graph would look like this, and my y-intercept would be at 0, 1. The asymptote, or the line that I cannot cross, is again a horizontal line, which is always y equals, specifically y equals 0 this time. That's the line I can't cross. My domain is negative infinity to positive infinity again, because the graph goes all the way to the left and all the way to the right. My range, bottom to top, the lowest value that my pen here is going to hit is 0, not included, and it goes all the way up to infinity again. So my range is 0 to infinity. And again, to point it out, the asymptote and the range have a connection, that these numbers are always the same. Does the above graph represent exponential growth or decay? This time it's exponential decay for really 2 reasons. One, because you can see the graph decreasing from left to right, and also because the base is less than 1. In the previous example, the base here was larger than 1, which makes sense why it was growth. All right, guys, so here's another chance to pause your video, and I'm going to start again with video number 3 with number 16. Thanks.